Okay, welcome to one of the last talks of GADEPS, because after September, the structure will change. Today we have Adrian Langer, who is going to talk about non-abelian Hodge theory, positive characteristic and its application. So, Adrian, please.
Thank you. Thanks a lot for the invitation. Unfortunately, you didn't invite me in person, which is a pity. I would really gladly come to Rio.
It will happen soon. As I said, there will be GADEPS conferences, actually.
Okay, I'm going to talk about this non-abelian Hodge theory, but I'm going to start with this non-abelian Hodge theory over complex numbers, as I guess you really are more familiar with complex manifolds than with positive characteristic story. But then I will try to explain how things like that look like in positive characteristic and how one can apply them to various things in positive characteristic, but also to characteristic zero problems. So so the first part is non-abelian Hodge theory over complex numbers. And I'm going to start with something, completely, elementary. You can't talk about non-abelian Hodge theory without some semi-stability notions. So I will need to fix some smooth projective variety with an ample divisor. So, for example, we take a hyperplane in some projective space in which X is embedded. And then we can define a slope for vector bundles, or more generally for coherent sheaves, just by saying that we take the degree of this sheaf and with respect to this hyperplane and then divide by the rank. So it's the same as taking the first chain class, which for torsion-free sheaves is just class of line bundle, and then intersect it with this hyperplane. With a general curve section coming from this embedding, and then divided by the rank. So when you have this, now when you can talk about semi-stability, and you say that your sheaf is, or vector bundle is slope semi-stable for every subsheaf, the slope of the subsheaf is less or equal to the slope of your sheaf. Okay, so that's obviously a very well known story, and I'm going to talk about the Higgs bundle case. So it will be quite similar. So now, but I'm going to say, well, what's a Higgs bundle first? So if we have a complex projective variety, or really I don't care whether this is complex or not, it can be any smooth projective variety over some algebraically closed field with an ample divisor. So in this case, a Higgs bundle is just a pair consisting of a torsion-free sheaf or vector bundle, but when I really define a Higgs bundle as rather like a Higgs sheaf and not a bundle. So this is a torsion-free coherent sheaf, and then with O of X linear map from your sheaf to sheaf tensored with one forms on your variety. And this should satisfy some kind of integrability condition. So, but saying that theta wedge theta is equal to 0, this roughly speaking is saying that we can consider this sheaf as a module over the symmetric tensor algebra of the tangent bundle on your variety. That's another way of looking at this. And then one can define notion of semi-stability in the same way as before, except that now we don't consider all subshifts, we simply take subshifts that are preserved by our Higgs field. So we should really have a Higgs subshift of our Higgs sheaf. And if for all Higgs subshifts we have this inequality for slopes, then we say that this is slope semi-stable. And there is also a notion of stability, which says that if we take but we have strict inequality for subshifts of rank that are strictly smaller than the rank of our sheaf E. Okay, so in 80s, at the end of 80s, there were papers of Hitchin in the curve case and also in Simpson in the higher dimensional case. They proved that every stable Higgs bundle has a Hermitian Young-Mills metric. And here I really mean a vector bundle, not some coherent sheaf. Anyway, the case where there is no Higgs field was known much earlier. So first, Narasimhan and Seshadri showed the correspondence between stable vector bundles on a smooth projective curve and unitary representations of the fundamental group, and then it was generalized by Donaldson and Uhlenbeck-Yau to higher dimensions, and yeah, so without Higgs field, this result was known, but the interesting story was that this works also in case of non-zero Higgs field, and then there is some correspondence that I call for simplicity Simpson's correspondence, but in fact it takes into account several different correspondences like Riemann-Hilbert and so on. So what this correspondence says is that if we have a smooth complex projective variety, then we have essentially equivalence of various categories. First of all, the category of representations of the topological fundamental group of the manifold underlying our algebraic variety, and we take representations in say GLR, where R, say that R is fixed, and then from every such representation one can easily produce a flat vector bundle. So you simply take the corresponding local system, and you if you have a local system, then it easily produces you a C infinity vector bundle with some connection, and then you can also get from this holomorphic vector bundle with holomorphic flat connection. And in the case of projective varieties, you essentially have Gaga theorem saying that this corresponds to algebraic vector bundles with flat connections. So this can be thought of, so this correspondence between the first and second categories is something that's called Riemann-Hilbert correspondence, and it can also be greatly extended in various ways that I'm not going to talk about. But the most interesting for us is the correspondence between flat vector bundles and semi-stable Higgs bundles with vanishing rational term classes. So hopefully you can still hear me because I can't see you.
Go ahead. We are here.
Okay, you are here. Great. Just checking whether if the connection broke, I wouldn't know. So
actually, okay. I want to ask this hyperplane. What is the role of the hyperplane? H.
Okay. So here there is. I mean, this doesn't play any role at all in a way, because semi-stability for Higgs bundles with vanishing rational term classes, it is you get the same notion for every polarization, for every choice of embedding of your variety into projective space. You still get the same notion of semi-stability. But this is a kind of accident coming from the fact that the chain classes of your vector bundle vanish. So obviously if you have a vector bundle with flat connection, then the chain classes vanish in the de Rham cohomology, and this is simply saying that what you get, the topological structure of a vector bundle is still the same, but you somehow give it a different algebraic structure with some different, and you change the connection to Higgs field. So is it okay?
Okay.
Okay, so the polarization of this hyperplane that I talked about, it will play some role later on, but you will see it. Okay, so one more remark is that this correspondence is factorial with respect to morphism. So if you have a morphism and say you take a vector bundle, flat vector bundle on X, and you pull it back to Y, but you still get a flat vector bundle. And if you do it the same for Higgs bundle, you still get a Higgs bundle. And these pullbacks, they still correspond to each other if your flat vector bundle corresponds to this Higgs bundle. So this is with respect to morphism and pullbacks. That's what I mean. Okay, so now I will recall some semipositivity theorem due to Griffiths. This is essentially a baby case of something much more general, but I'm going to give you just some simple ideas of things that you can prove, and I'm not going to talk much about generalizations at the moment. I will give far-reaching generalization later on. But let me give a proof of this theorem, because it's very easy. So the theorem is saying that if you have a smooth morphism between smooth complex projective varieties, then if you take higher direct image of the relative canonical bundle, then this is a Neff vector bundle. So Neff vector bundle means that the degree of this vector bundle on every curve inside of X is greater or equal than 0, and the degree of every quotient of this vector bundle is still on this curve is still greater or equal than 0. So how do we prove this? So we need to this is really non-abelian Hodge theory in this case. So if you take the higher direct image of the constant sheaf on the identification of our variety Y, then this underlies, this corresponds to a local system which underlies some flat vector bundle, which in this case is a complex polarizable variation of Hodge structure. So this really means that we have this V, a vector bundle, this nabla, which is a connection, and F bullet, unfortunately bullet was left on the left side. So here what I mean is that we really get a Gauss-Manin connection on the higher direct image of the de Rham complex in this case. So and this comes with some Hodge filtration. And the funny thing is that in this case, this filtration is Griffith's transverse and Simpson's correspondence for complex polarizable variations of Hodge structure. It produces very special Higgs bundles that are systems of Hodge bundles. What we do in this case, we simply take the associated gradient of this higher direct image, and this Gauss-Manin connection, it induces a Higgs field in this case. And this, what we get is simply a semi-stable Higgs bundle with vanishing Chern classes, as expected from Simpson's correspondence. So now we look what happens when we restrict to curve. So we consider any morphism from a smooth projective curve to our variety X, and then we take the pullback of our Higgs vector bundle. So what we get is still semi-stable Higgs vector bundle of degree 0, and it corresponds to the pullback of this flat vector bundle V nabla. And then, well, if we take the quotient of higher direct image of the relative canonical bundle, then you immediately see that that this higher direct image of this relative canonical bundle, it's really a quotient of your Higgs vector bundle E theta, but now the theta on this term vanishes. So if we take now the quotient G of this vector bundle, then it produces a map from the pullback of this Hodge of this Higgs vector bundle to G with 0 Higgs field. And now semi-stability simply says that the slope of G is greater or equal than the slope of this G upper star E theta, and that means that the degree of G is greater or equal than 0. And so any quotient G of this vector bundle is non-negative. So that's a very easy proof, but it somehow shows how things can be made in much more general setup. So there is a theorem of Bruneberg that somehow goes in the same direction and greatly generalizes Griffith's theorem. So what you start with is a smooth complex projective variety with a simple normal crossing divisor D on this variety, and then what the theorem says is that if you have a polystable logarithmic Higgs bundle, so logarithmic means that it's taking into account this simple normal crossing divisor D. So the map theta is now from E to E tensored with logarithmic 1 forms on X with poles along this divisor D. So if we now assume that this E is he had this condition of being polystable, which means direct sum of stable with the same slope. But then, if we assume that E has vanishing rational Chern classes, and we take a subshift of the kernel of this Higgs field, and moreover we assume that this subshift is locally split in our original vector bundle, then the dual of this vector bundle is Nef. So this is really a direct generalization of this theorem due to Griffiths, except that it works in the logarithmic case, and the proof that I gave you, it's no longer valid as it's written, because the problem is that everything would work except for the fact that this morphism from C to X could land inside our divisor D, and then we cannot say what is the pullback of a Higgs vector bundle, this logarithmic Higgs vector bundle to this curve. So this is really a serious problem that appears inside with this proof, and he used nearby cycles to prove this. So now the positive characteristic remark first. So the first remark is that, well, everything fails. So you don't have any correspondence between flat vector bundles on varieties in positive characteristic and semi-stable Higgs bundles, simply because flat vector bundles in positive characteristic were far too many of them, and they don't need to have vanishing chain classes. That's one reason. Another problem is that even with this Griffith's theorem that we had, if we consider some algebraically closed fields of characteristic P, when Moret-Bailly constructed a smooth family of abelian varieties over a projective line, such that the direct image of the relative canonical bundle is O of minus n direct sum O of P n, where n is n a positive integer, essentially. So obviously this direct sum has O of minus n as a quotient, so it is not Neff. And Griffith's theorem, as you see, fails. So there are various reasons why essentially nothing from non-abelian Hodge theory can work in general in positive characteristic. And this is, well, just one example why things fail. Any questions?
So this here is n in any number, no? Just this small n.
It can be any number, n, really. 1, 2, up to whatever. Can be arbitrarily large. So actually it is easy to see that once you have one example, when you have lots of other examples also by base change, but yeah, more or less using relative Frobenius or things like that. Okay, so he constructed this example in a quite funny way, taking some quotient of P1 with an abelian variety by some non-reduced finite group scheme, like in a rather funny way inside of this abelian group, abelian variety surface in this case.
So all the
I should say that these are
all the abelian varieties in this family. They are isogenous, then, no?
No, we are not isogenous.
You said finite quotient, but you were.
Yeah, but finite quotient by an abelian group scheme, so they are non-isogenous anyway. So being isogenous is up to Etal
Okay.
covering. So and here, I really should say that these are surfaces, as you can see from the fact that the direct image has rank 2. Okay, so the positive characteristic story will be somehow similar to Simpson's correspondence between Higgs vector bundle and modulus integrable connection, but it will be more complicated. So if I have an algebraically closed field of positive characteristic P, then I consider first the category that I denote by this Higgs P minus 1x. So this is the category of Higgs modules, now E and theta, where theta to the power P is equal to 0. So it means that the Higgs field is nilpotent of level P, say. And this is related to these complex polarizable variations of Hodge structures. If you think about complex polarizable variations of Hodge structure when we associated as associated Higgs bundle you have a system of Hodge bundles, and this means that the Higgs field in this case is also nilpotent. So so this is just a part of the category of all Higgs modules which we consider. And then there is another category, which is the category of, well, essentially flat vector bundles, but we consider the category of X modules with an integrable connection. And there is a notion of p curvature in this case, in positive characteristic, that I'm not going to talk about. For every integrable connection, there is some kind of p curvature, and we require this to be nilpotent of some level less than p, so of level p minus 1 again. So the basic theorem that was proven around 2007, I think, is saying that if you have a smooth variety and you assume that this variety is liftable modulo p squared, then there exists an equivalence of categories between these modules with integrable connection with these nilpotence conditions that I talked about, and Higgs bundles with these nilpotent conditions. But you see here, it is quite funny because this smooth variety can be possibly non-projective. You have a lifting to the ring of bit vectors of length at most 2. So in case, say, when you had, say, fp, then you would lift it to z modulo p squared, but you can do this for any algebraically closed field and then lift it modulo this p squared. This w2 of k has characteristic p squared and not p. If you assume that such a lifting exists, then every lifting produces one equivalence of categories, which is called the Cartier transform, but various liftings, they can lead to different equivalences. So it's not like characteristic zero story. And another problem is that there is no semi-stability notion involved here because, well, varieties are possibly non-projective. And it's not so good because it seems like it's not so easy to use this to prove any geometric facts like the one I talked about, semi-positivity things or whatever. So this is a kind of Simpson's correspondence, but it's not yet what we want in a way. So another thing that we want is somehow more complicated. So if we have now a smooth projective variety in positive characteristic, then we can talk about semi-stable Higgs modules. So say that E0 theta 0 is a semi-stable Higgs module on our variety X, and then one can define so-called Higgs-Derham flow in the following way. So suppose that we start with a Higgs bundle with nilpotent Higgs field of like the one that we use for our Cartier transform. Then the inverse Cartier transform produces us all of X modules with an integrable connection, and actually it is because we have equivalence of categories, it is still semi-stable, but now with respect to the connection. And then the point is that one expects that this on this vector bundle with integrable connection, we have some Griffith's transverse filtration, which is called SI in this case, such that if you look at the associated gradient, then what we get is a semi-stable Higgs module in this case. And then we repeat the procedure. We take the, well, this semi-stable Higgs module is still a system of Hodge bundles or Hodge shifts. So the Higgs field is nilpotent, so we can use the inverse Cartier transform to produce another vector module with, well, O of X module with integrable connection, and then find the filtration and so on. And then we have an infinite sequence like this, which I usually call the Higgs-de-Rham sequence, but it is also called Higgs-de-Rham flow. The problem is that it's not so clear that these things exist. So some years ago, Lan, Schenk, and Zuo conjectured that it should essentially always exist if you have a lifting of your smooth predictive variety modulo p squared, and that's what they proved with Young, and I proved this independently using somewhat different method. So the theorem says that if you have a semi-stable Higgs module of rank R less or equal than P, then it admits a canonical Higgs-de-Rham flow. So here I really can start with any semi-stable Higgs module, and I can produce from this E0 and theta 0, which is a system of Hodge bundles, which is semi-stable, and then have this kind of flow. Hopefully it's not someone saying that you can't hear me. Okay. So and then the same theorem holds in the logarithmic case. If you have a small predictive variety with a simple normal crossing divisor, and you assume that there exists a lifting of this pair modulo p squared, then every semi-stable logarithmic Higgs module admits a canonical Higgs-de-Rham flow. And here the funny thing is that there is no assumption on Chern classes of Higgs shifts or these modules with integrable connection. So it's not exactly like in the characteristic zero case where you had a correspondence between flat vector bundles and Higgs, semi-stable Higgs vector bundle with vanishing Chern classes. But it's actually quite good that it's not like this, because there are some applications that actually use the fact that we can say something about shifts with non-zero Chern classes. So yeah, so the first one is Bogomolov type inequality. So if we have smooth predictive variety with a simple normal crossing divisor in positive characteristic P, then if you assume that this pair is liftable modulo P squared, and you have semi-stable logarithmic Higgs bundle of rank not greater than the characteristic of your field, then the discriminant of your E is greater or equal than 0. And here you see that this is really slope semi-stable with respect to some fixed h, and this h really appears here because this class, this discriminant is 2 times the rank times the second Chern class minus rank minus 1 the first Chern class squared. It's some class in the codimension 2 cycles on your variety, and then you can intersect codimension 2 cycle with a general surface, complete intersection surface, and get a number. And this number is greater or equal than 0.
Just to be sure. So theta has logarithmic poles along D, this normal crossing divisor.
Yes.
Okay.
Yeah. So yes. So this is, I mean, obviously we can take d equal to 0 and then we will have just usual story, but the logarithmic story, I didn't mention this. The logarithmic Simpson correspondence is also known, and it is due to Mochizuki, but Takuro Mochizuki, but he had to work really hard, and it's not like the methods of Simpson, which were analytic, but they work easily in the logarithmic case. Whereas with these kind of techniques that you have in positive characteristic, it's quite funny to see that there is essentially no difference between considering a variety or a pair of a variety with a divisor. So everything is the same. And for example, this theorem, it tells you that if you have smooth complex projective variety with a simple normal crossing divisor and a semi-stable logarithmic Higgs bundle, then this discriminant is greater than 0. So in the non-logarithmic case, this was first proven by Simpson using analytic methods. And actually, Narasimhan many years ago wanted me to work out an algebraic proof. That was about 99, but I was able to do this only in the rank 3 case, and another postdoc that was at the time at ICTP was doing the rank 2 case. And that's it, but there was no algebraic proof, and with this technology there is an algebraic proof of Bogomolov type inequality for Higgs vector bundles, and actually even in the logarithmic case, in the characteristic 0, it follows immediately by spreading out. So it's kind of fun application. Another thing is that one can generalize this Bruneberg's theorem that I was talking about. So now I consider the category that I denote by this min Higg 0 for some reason. So this is the category of semi-stable, locally free, logarithmic Higgs sheaves of rank lesser than P with vanishing Chern classes in L-adic cohomologies now. Or actually, it is sufficient that that numerical Chern classes vanish in this case. Then if we have X, then I consider an irreducible component of this simple normal crossing divisor D. So this is, let me call this Y. This is some smooth variety, and then I can subtract from D this component Y, and when I have a divisor that I can restrict to Y and get divisor that I denote by dy. So the basic theorem that just appeared this year is saying that if you have semi-stable locally free logarithmic Higgs sheaf like this, then when you can restrict to this irreducible component, and if you have this restriction, then this is still semi-stable, but it is not Higgs sheaf anymore. It's rather a module over the symmetric algebra of the restriction of the logarithmic tangent bundle to your component Y. So let me recall that saying that E theta is a Higgs sheaf could be reformulated by saying that this is a module over the symmetric algebra of this logarithmic tangent bundle. But now if we restrict, then this is the semi-stable module over this algebra of symmetric algebra of the restriction. And then, well, it really comes with a filtration such that the associated graded is still semi-stable, locally free logarithmic Higgs sheaf on this restriction. So I summed this up by saying that this restriction can be deformed to an element of the same category, but now on this irreducible component y, on this restriction. And once you have this, then it is pretty obvious to see that you can restrict to curves and you still get some semi-stability. And then this really generalize Brunner-Barb's theorem. Even in characteristic 0, you get out of this a new result that was not known before. So it's really much stronger than what Brunner-Barb did.
So this is still our characteristic P field.
Well,
This
up
theorem.
there, yes, but down there, no. So the theorem in the characteristic 0 case, it's also the same. So if you have semi-stable locally free logarithmic, or essentially semi-stable logarithmic Higgs vector bundle with vanishing rational term classes, then the restriction to any reducible component of your divisor is semi-stable as a module over the symmetric algebra of the restriction of the logarithmic tangent bundle. And this is also, it doesn't really matter whether this is characteristic P or characteristic 0. Characteristic 0 version follows immediately from characteristic P. So here I didn't say exactly what are the assumptions on XD, but but it is either in characteristic 0 or it is in positive characteristic, which is liftable modulo P squared. Yeah. So this is one thing. But the main problem that appears in the proof of this result is local freeness of these things that appear in the Higgs de Rham flow. Let me go back here. So the flow is like this. You start with a vector, even if you start with a vector bundle E0, you take this equivalence of categories, you get still a vector bundle V0. Now you have some filtration, and the associated graded is not a vector bundle anymore, this E1. And this really causes a problem because now you cannot restrict to, say, curves which pass through the torsion or the cotorsion of your sheaf. So you cannot restrict to curves that pass through the points where this E1 is not locally free. So the main idea is that if E0 has vanishing term classes, then if you take this V0 and E1, then E1 is still locally free. So this result is a bit delicate, and that's the main problem that appears in proofs, and this can be resolved, roughly speaking, by the following theorem. If you have a slope semi-stable logarithmic Higgs sheaf with vanishing first and second term character, and if you assume that this sheaf is reflexive, or the normalized Hilbert polynomial of this sheaf is the same as the Hilbert polynomial of the structure sheaf, then these assumptions imply that your sheaf is actually locally free. And actually, from the vanishing of first and second term character, it follows that all the term classes of your E vanish. one can do even slightly better and saying that if you have a Jordan-Helder filtration, then elements of this Jordan-Helder filtration are also locally free. So this can be somehow summarized by saying that you have a filtration whose quotients are locally free, slope stable, and have vanishing Chern classes. Okay, so that's more or less the main problem that appears in the proof, but this theorem in the characteristic 0 case for the non-logarithmic, in the non-logarithmic case was known by Simpson over complex numbers, but he used this functoriality of Simpson's correspondence and Lefschetz type theorem. So, and nothing like that can work in positive characteristic. On the other hand, when you have this result, you also get the same result in characteristic 0. And even in the logarithmic case that was not known. So this is one thing, local freeness. And now I'm going more or less towards the end of the talk, I think. So I'm going to talk about possible generalization of these results to singular varieties. So nowadays the complex story is more or less known, at least in the case that is not logarithmic, as I will just explain in a second. So actually, this is how the authors formulated the result, but I have no idea why this is formulated this way, because this D doesn't play any role. Anyway, if you have a smooth smooth normal projective variety with an effective divisor D, then Grebke, Bekus, Paternal, and Tadji, they proved that if your pair has Kawamata log terminal singularities, and if you have a stable reflexive Higgs sheaf on your on this X, then this discriminant has non-negative degree on every general complete intersection surface. Okay, so this is the result that they proved, and they also proved some kind of Simpson correspondence in case of varieties with Kawamata log terminal singularities. It's a bit more subtle than it looks because it's not completely obvious what is this discriminant. I mean, it was something in combination of the second Chern class and the first Chern class squared. But the problem here is that if you have a reflexive sheaf on a normal variety, then it's not clear what is the second Chern class in this case. But fortunately, they assume that this variety has KLT singularities, which implies that the singularities are a quotient in codimension 2, and then you can talk about orbifold Chern classes, and that's exactly what they are using for this one. And as I said, they also can say what happens if these orbifold Chern classes vanish on varieties with KLT singularities. So, but this works only for Higgs sheaves and not in the logarithmic case. And what I'm doing right now, and it is not yet available completely. I mean, not, at least you can't see the paper on the archive, then is the following result. It's saying how you can possibly generalize this kind of simple Simpson correspondence or to singular varieties in positive characteristic. So if you have a normal projective variety with an effective divisor, which is just a sum of some prime divisors with coefficients equal to 1, then I proved the following result. If you assume that this pair is, well, you can assume that this is liftable modulo p squared like before, but this is not really necessary. You need something slightly weaker that I call almost liftable. And if you assume that the singularities of this pair are also almost locally f-liftable, meaning that they are liftable together with the Frobenius morphism modulo p squared, then in this case, if you have a semi-stable reflexive logarithmic Higgs sheaf, then the discriminant is still greater or equal than 0. And this implies this result that I just stated, but not always. The problem is that it's not exactly true that if you have something that is KLT in characteristic 0, then its reduction is locally f-liftable. Or almost locally f-liftable. This is unfortunately not true. So this is slightly different class of singularities that you get. And also you run into lots of troubles with this result because you don't know what's the discriminant. And it can be solved so easily as saying that you take only for chain classes because we allow various other kinds of singularities. So for example, in the surface case, we can, what you get are linearly reductive quotients, meaning that you take locally something smooth and you divide it by a linearly reductive group. But then you don't want to assume that this group is finite. So it's something slightly different. This kind of singularities are f-regular. But yeah, I also allow, for example, cones over an ordinary elliptic curve. So these kind of singularities are also locally f-liftable. And then you are in much more serious trouble because these orbifold chain classes, they certainly don't work. So you need to first of all define what are these kind of invariants, these chain classes that appear, and then and only then you can talk about these inequalities. And also you can say what happens in case where the discriminant is equal to 0 and things like that, but I'm not going to talk about this anymore. So I think that's more or less what I wanted to
Okay, thank
say.
you, Adrian. So I stopped clapping at some point because digital